In our previous lesson, we looked at writing the equation of a line or a linear function using the slope-intercept form, in which we knew the slope, which was represented by the letter n, and the y-intercept, represented by the letter b. Today, we're going to look at another way to write the equation of a line, and specific cases of writing that. Today, we're going to look at another form of writing the equation of a line called the standard form. Now, this is applicable when we come across situations that involve linear combinations. So, a linear combination is simply an expression in which all variables are raised to the first power, and neither of the variables are being multiplied or divided by each other. So, an example would be the situation in which I had d number of dimes, now a dime is worth 10 cents, plus q number of quarters, now a quarter is worth 25 cents, and I know that they must add up to equal $5. So let's say I have these $5 in change. The change consists of dimes and quarters. This is a linear combination of dimes and quarters that add up to equal $5. So this is considered standard form of equation, where ax plus by equals c. Now you'll notice that y and x are still a part of the equation of a line. A, b, and c are all going to represent constants or numbers, such that a and b are not equal to 0. So an example of this would be something like 2x plus 3y is equal to 7. This is an example of this of a linear equation in standard form. All right, let's take a look at our first example here of linear combinations. We see that in a professional hockey game, the winner gets 2 points, a tie is worth 1 point, and losing is worth 0 points. So early on in the season, a team has 11 points. We want to write a linear combination that represents the relationship between the number of wins, losses, and ties. So I'm going to assign W for wins, L for losses, and T for ties. Let's write that equation. Here's what it looks like. 2 times the number of wins, so that's 2 times W, plus 1 times the number of ties, plus 0 times the number of losses. Now, that should always be equal to our total points. Well, in this case, our total points are 11, and also in this case, 0 times anything would just cancel itself out. So let's simplify this equation to 2W plus 1T is equal to 11. Now, let's come up with all the possible outcomes of wins and ties that could have occurred. Now remember, wins and ties, the points always have to add up to equal 11. So let's say we had 0 wins. Therefore, we must have had 11 ties. Or we could have had 1 win, in which case we would have had 9 ties. 2 wins would result in 7 ties. 3 wins would be 5. 4 wins would give me 3, and finally 5 wins, I would have 1 tie. Now I couldn't possibly have 6 wins because that would put me at 12 points, and that would put me over my max. All right, let's take a second to plot this now. Now, the reason why I'm not connecting these points is that I cannot have a fraction of a win. These are actual individual points, and when we just graph the points of a function, then this graph is going to be called discrete. In other words, it's not going to be continuous. The continuous graph would be a solid line drawn through all those points, indicating that even fractions in between those hard points there would be possible outcomes. But they're not in this case. We can only have whole number outcomes. All right, in our next example, we're at Harry's hamburger joint, and a hamburger costs $2.50 and a hot dog costs $2. We're going to eat out and we're going to spend $30. Well, we want to write a combination, a linear combination here, using B for hamburgers, the number of hamburgers that we purchased, and D for the number of hot dogs. So let's start off by writing that linear combination. It costs $2.50 per 1 hamburger, plus $2 per 1 hot dog, and I know that the total I spend has to add up to equal $30. Part B of this problem asks us to solve this equation for D. That means to isolate the variable D. Rewrite this in terms of the variable D. So we're going to start by subtracting 2.5b from both sides. We'll end up with 2d is equal to 30 minus 2.5b. Now we need to divide 2 off of both sides, and when we do that, we have d equals 15 minus 1.25b. So this could look familiar to you. It should look familiar to you. This is now written in y equals mx plus b, or slope-intercept form. All right, part C of this problem asks us to identify all the points that would correspond to actual combinations of hot dogs and hamburgers. Now, in order to do this, we're going to use our graphing calculator. So take out your graphing calculator now, and we are going to enter into our y equals, our function editor here, this function where y is going to be equal to d, the number of hot dogs, and x is going to be equal to b, the number of hamburgers. So I will enter in 15 minus 1.25x. And now I'm going to go to the graph of that function. So there's the graph. It slopes down and to the right. However, I don't really want the graph of that function. What I'm going to use is the table. So I'll hit second function, graph, and now I'll go to the table. And this table, remember, is going to produce for me all the combinations of hot dogs and hamburgers that I could purchase. However, I'm only going to be looking for the ones that produce whole number results. So let's take a look at this first one here. This first one says I could purchase 0 hamburgers and get 15 hot dogs. So that's a possible combination. I will put B here for burgers and D here for dogs. So if I go 0 burgers, I could get 15 hot dogs. Now the next one the table says 1 and 13.75. This is not an actual outcome because I can't buy 3/4 of a hot dog. So I'm only looking for the whole number combinations. The next one in my list is 4, 10. So I could buy 4 burgers and 10 dogs. Now I'm going to keep scrolling down here on my calculator to see what our next whole number combination is. And there it is right there, 8 and 5. So I'll write that into my list. And then finally, the last combination I could purchase would be 12 burgers and 0 hot dogs. So those are all of the possible combinations of hot dogs and hamburgers I could purchase for $30 at Harry's Hamburger Joint. All right, let's take a look at an example from a chemistry lesson. Now, this is pretty important when we start to mix solutions in chemistry. We always want to make sure that we have the final solution mixed to the proper amount. So you'll actually use linear combinations quite a bit. It says here that you're going to mix X liters of 1.5 moles of acid with Y liters of 6.5 moles per liter solution. The final mixture needs to contain 15 moles of acid. So let's write out that linear combination. We have 1.5 moles of X liters plus 6.5 moles of the Y liter solution. And together they have to combine to give me 15 moles of acid. So there's our linear combination relating X and Y. It says now in part B how many liters of the 6.5 solution needs to be added to 5 liters of the 1.5 solution in order to get 15 moles. Let's go ahead and we're going to substitute in our 5 for our into our equation here for X. So we'll end up with 1.5 times 5 liters plus 6.5 times our Y, which is what we're solving for, is equal to 15. This gives us 7.5. Now we're going to subtract that 7.5 over to the other side to get rid of it on this side. So 6.5 is now equal to 7.5, and now I have to divide both sides by 6.5. So in the end, Y, or the amount of solution here, will come out to be 1.153 liters.